Okay, so this is, I think, a beautiful and deeply understood theory, and somehow I have 15 minutes. So I would like to maybe describe one example which at least the experts understand rather well, and then maybe I'll try to point out some things which I at least do not understand, and we'll see where that leaves us. Okay, so this is, uniform spectral gap. Infinite area. Okay, so my basic topic of study is going to be somehow finitely generated subgroups of SO21, SO21Z. So I'm thinking of these guys as acting on Z3, and I'm thinking that they preserve the standard sort of Pythagorean form. And as I say, I want to assume finitely generated. I want to assume no torsion, and I want to assume not virtually cyclic. So roughly speaking, I don't want to say this is just all powers of some single element. And the basic question I'd like to ask is sort of orbit counting, and I'd like to try to do sort of number theory on the orbits of these guys. So maybe I set W is equal to sort of standard boring Pythagorean triple. And I look at maybe two questions. Maybe the vanilla orbit counting question is n of t is just how many orbit points are not too big. Maybe the less than t in the usual norm. And then if you want to do number theory or number theoretic questions, then a natural one might be this. How many of these guys are not too big? And maybe, so every guy in this orbit is, of course, a Pythagorean triple. It corresponds to some Pythagorean triangle. So maybe I'd like, if I'm really optimistic, I might like to ask this guy to be prime. And this is perhaps naive, which is to say I have no idea how to do this. But maybe a weaker question would be to ask this guy be almost prime, which is to say it doesn't have too many prime factors. When I write out its prime factorization, I only vote out R primes. So I'll call this guy MRT. So I'm supposed to tell you something about spectral gap. Yeah. W is just this vector. It's just a. I hope I have not said anything deep yet, but we'll see. Okay, so I should give you one piece of notation. So if you're used to thinking about infinite area, okay, so I don't assume that this guy is a lattice. And in particular, it probably has infinite covolume in SO21R, or it's equivalently, it's probably infinite index in SO21Z. And if you're used to thinking about these things, you know that delta gamma equals, I'll write it as delta, if the critical exponent is an important number. And this is just essentially it's some parameter which, as I've set things up, it's always going to be strictly positive, and it's always going to be at most 1. And it measures, how close I am to being a lattice. So if I'm very, very close to being a lattice, delta will be very, very close to 1. If I'm an extremely sparse group, it'll be very close to 0. And I'm 1 exactly if I'm a lattice. This Hausdorff dimension of a limit set, yeah. So if you know what that means, then that's great, and if you don't, then don't worry about it. I mean, obviously you do. Okay, so then this sort of spectral theory I said was supposed to solve my problems. So what we do is we look at the sort of X is going to be the hyperbolic manifold associated to this guy. So of course, R3 contains a sort of copy of hyperbolic 2 space. Gamma acts isometrically on it, so I can form this quotient H2 over gamma. This is a hyperbolic surface of probably infinite area. And it turns out that what we care about is the hyperbolic Laplacian on this guy. And it turns out that we understand the spectrum of these guys fairly well under an assumption. So delta greater than a half is what I want to do. So things which are sparse but not too sparse. And under this assumption, we have lambda naught, the base eigenvalue, base sort of L2 eigenvalue is delta times 1 minus delta. And also we have a gap. There is a gap in the spectrum. So which is to say that there exists epsilon greater than 0 such that this open interval lambda naught plus epsilon doesn't meet spec R. Meet spec. Okay.
How does gamma act on the upper half plane? Do you identify SO21 with SL2?
Well, yes is one answer to this, or I can think of the upper half plane sitting inside R3, right? There's a standard embedding,
Okay.
Which is x squared plus y squared minus z squared equals 1 or something like this, if I remember correctly. Okay? Okay, so we understand the bottom of the spectrum of this guy, and we understand some notion of spectral gap for this guy. And there's a sort of there's a beautiful theory developed by people like, I should say this is Lax Phillips maybe, building on work of Patterson, I guess. And there's a beautiful theory which says that this is enough to solve my orbit counting problem. So it turns out that this implies, and you could see, say, a paper of Kontorovich. I should say, what I'm saying at the moment is not state of the art. People in this room understand it, I think, much better than anything I'm saying now. But Kontorovich will say, for instance, that this implies that at least n of t is some constant times tetra delta plus O of tetra delta minus epsilon tilde, and this epsilon tilde somehow should come from this epsilon. Okay. So we have an orbit counting problem, and we think we can solve it by understanding something about spectra. We think it has something to do with spectral gap. And the difficulty is the spectrum of this guy doesn't understand what a prime number is, as far as I can see. There's nothing going on here. So maybe we should pass to a congruence cover, and maybe that will teach the spectrum what a prime number is. So gamma of Q should be the congruence subgroup. So this is an integer subgroup of this guy, so just guys who are congruent to identity mod Q. And then X of Q is gamma of Q mod H2. And this is, of course, a finite cover of X. And I can have, the hyperbolic Laplacian on this guy. And I can have the base eigenvalue of this guy as well. And what's somehow remarkable, so Lax Phillips, if I apply this Lax Phillips to these guys, what I should say is that, well, now lambda naught of Q turns out to be equal to lambda naught. This is not so hard. And it should say that there's an epsilon Q greater than 0 such that this happens doesn't meet epsilon Q. And what's somehow remarkable is that this epsilon Q doesn't depend on Q. Okay? You have a gap in the spectrum, and it is uniform. This is what we mean by uniform spectral gap. It's not so complicated. So this is maybe some combination of Bourgain, Gambert, and Sarnak. So Bourgain, for instance, gives you an explicit spectral gap if I'm willing to assume that delta is really quite close to 1, maybe bigger than 5/6. So these guys have understood this. And what does this do? Well, it means that I can solve counting problems for the congruent subgroups with sort of uniformly good error terms. And this gives me a chance to apply sieve. So if I can do these things, I can maybe throw away, I want to find somebody whose hypotenuse is almost prime. Maybe I start with everybody whose size is less than 1 trillion. I throw away guys whose hypotenuse is divisible by 2 or by 3 or by 5. At every stage, I knew how many things I threw away. So maybe there's a reasonable hope, and indeed you get it. So this is enough to show. This is again the same. For instance, it's in the same Kontorovich O paper that this MR of T is at least somehow up to constants. It's at least as big as you would expect it to be. Okay, so this is some sort of in the direction of a prime number theorem for these guys. And I should say that maybe they weren't quite so interested in this. What they were most interested in is giving a nice explicit value for R. So it turns out that if R is bigger than, maybe it's 0.9992. Sorry, if delta is bigger than 0.9992, then maybe R is at least 14 would turn out to be enough. So if you have explicit spectral gap, then you have explicit numbers here, though maybe don't quote me on those from memory. Okay, so this I think is a very pretty picture, and it's been well developed by people. There are things which we find difficult about it, though. So for instance, I assumed here that delta gamma was big. What if delta gamma is small? If we're going to look at sparse subgroups, we ought to look at really sparse subgroups, and we ought to understand them. And the difficulty is that for small delta, well, this Lax-Phillips theorem, well, Lax-Phillips still understood everything, but what they said is there's no base eigenvalue and there's no spectral gap. There's pure continuous spectrum, so everything that we were trying to do here is going to blow up in your face, and there's really nothing you can do about it. These lovely arguments of Borg-Gamma-Zarnock, they were up to this challenge, and they introduced these congruence, or they use these congruence transfer operators, and they are able to get good enough orbit counting estimates to do sieve in any case, so this is really beautiful. And my advisor and I were interested in the question of, can we reinterpret this stuff in some other way? Can we slightly strengthen these results? So let me just spend 3 minutes trying to indicate a way we like to think about this stuff, and we think, might be a useful viewpoint, and then hopefully all will be done. So for small delta, what I'd like to do is think about dynamics. Okay, so as you mentioned, at this stage I'm going to start talking about gamma sitting inside SL2R, which I'm going to call G. And this is just maybe I take a pre-image under a double cover or something like that. Okay? And inside this group, I have my favorite AT is my favorite diagonal elements, e to the t over 2, 0, 0, e to the minus t over 2. And a very standard thing we might try to understand is maybe for phi and psi, say, smooth compactly supported functions on this quotient space, this group quotient space now. Maybe it would be a reasonable question to ask what happens to these things which look like matrix products, matrix coefficients. So phi of gt, psi of g dg, integrate over the natural space. Okay. And somehow when you look at this for the first time, you think you're doomed, because somehow the L2 theory we know is badly behaved, and so somehow if we're looking at these L2 matrix products, somehow things shouldn't be nice. But it turns out that this space is better behaved. So for instance, we know that the hyperbolic Laplacian restricted to this space is resonance-free on a half plane which is bigger than it somehow you would expect it to be in this case. And something nice here happens as well. So what we find is that this is some constant which depends on phi and psi, and then you get a decay term, and you get 1 plus O e to the minus something like this. And what I want to say is this main term you should think of as being corresponding to the bottom of the spectrum for the hyperbolic Laplacian. This gap, this sort of epsilon, this eta change in the exponent, this extra exponential decay, you should think of as being spectral gap. And the remark is, for there exists eta greater than 0 such that this happens independent of Q. So eta is not supposed to depend on Q. This is supposed to be spectral gap, which is honest in some sense. Okay, so this is something that my advisor and I tried to understand. And maybe I'll say 2 words about what's going on here. You want to understand this gamma of Q mod out by G. You want to understand this A action. Well, gamma over Q, G over gamma Q, looks an awful lot like, if you don't look too closely, it's a bunch of copies of the base space. So somehow a Cayley graph. It's a Cayley graph over the base space. And what we think ends up happening is that when I look at the AT action here, there's sort of somehow 2 regimes. You can look at long time scales or you can look at short time scales. And if you look at long time scales and you stare enough at the lovely arguments by Borg-Gamma-Zarnock, I think what you end up saying is that the this dynamics ends up looking like a random walk on this Cayley graph. And these Cayley graphs are very highly connected. And because they're very highly connected, they're what's called an expander family, and therefore we can understand them rather well, and we can get the kind of spectral decay that we want. So they don't say anything like this in their paper, but I think if you force it into this language, this is what you end up with. For our case, we're interested in the high-frequency behavior. So the observation is just if you're only working in short time periods, there's no time to move from one sheet to another. So you have basically 1,000 parallel copies of this base space, but we understand the base space, so the tools of hyperbolic dynamics essentially let you get at this. And since there's no mixing between the different leaves, you can hope to understand it just using those techniques times 1,000. Anyway, so this is a picture, for large delta we have a very nice picture, and people have done some very, very clever things. For small delta, at least I know much less. We think this is one way of thinking about it. Certainly congruence transfers are the first and maybe best way of thinking about it. I don't know what happens if I want to go to SO31 instead. You would expect the same things to work. Somehow the proof that we have, or the proof that I understand for this, is not necessarily the natural one, and I'd like to understand, is it something just about random walks in groups and the mixing of the base space? I don't know. Are there other things which are easy to understand? So the delta less than or equal to a half case seems to be easier to understand from a dynamics point of view than it does from a representation theory point of view. Are there other bits of this theory which are easier? And we think there might be, but I don't know. Anyway, that's, I think, all I have time for, probably. So thank you.